with that clear, let's tackle our question now. Okay, so let's draw whatever is given. It's given that there is a light string and it is attached. Okay, so let me draw that. So we have a light string somewhere over here. Here's a light string and it's attached to a thick rope. So here is thick rope. I'm going to show red one for thick rope. The speed of a wave in the light string is 200 meters per second. So over here, velocity is 200 meters per second. And in the rope is only 50 meters per second. Okay. A wave of 5 Hz frequency is created. So, alright. It's created in the light string. Right, so we have a wave and it's created with a frequency of 5 Hz. Calculate the change in wavelength and frequency when it enters the thick rope. So these waves are going to go and hit the rope, and once it hits the rope, we want to know what's going to happen to the wavelength and we want to know what happens to the frequency. Well, we can first calculate what's the wavelength here itself. It's V divided by F. We just found that out. 200 divided by 5, that is 40 meters. That's the initial wavelength, and we know what the initial frequency is. That's 5 Hz. That's a given. Okay, this is initial. The question is, what's going to happen once it enters the thick rope? Well, once the wave enters the thick rope, by the way, some of the waves will get reflected back, but don't worry about that. Some of the waves will get transmitted, and some of them will get absorbed also, but forget about that. Anyways, the waves will get now transmitted, and let's concentrate on the transmitted waves. Well, in the rope, let's do the final case. In the rope, we know the velocity is 50 meters. And remember what I told you? Frequency. Frequency of the wave doesn't depend on the medium. It is decided by the source. If the source says I'm going to create 5 Hz and you have 5 oscillations per second, just think over here. If this particle at the junction is oscillating 5 times per second, so this particle is connected to the next particle, which is of the rope, this particle of the rope must also oscillate 5 times per second. Continuity is needed, right? Is it possible that this particle at the junction, the left one, the blue one, oscillates 5 times per second and the one on the right oscillates at a different frequency? That's not possible because these guys are integral, they're connected to each other. So we can understand from here the frequency must remain the same. So frequency is 5 Hz. So what changes is the wavelength. I'm going to put a dash on this. Okay. Alright, so lambda is going to be 50 divided by 5, that's 10 meters. So the wavelength shrinks now. And the reason wavelength shrinks is because the frequency is the same, so oscillations are coming in, but the wave is not moving very fast. So the wave is moving very slowly. So if the wave over here, I did not draw the wave properly. So if the wave is over here this way, once it enters, the wavelength will shrink. Okay, so the question is, what's the change in wavelength? What's the change in wavelength and what's the change in frequency? Well, change in wavelength is final wavelength minus initial wavelength. That's minus 30 meters. And what's the change in frequency? Well, change in frequency is 0 because the frequency is independent of the medium. I hope that made sense to you. Okay, see you next time.